Welcome students. So from this application of derivative, let's solve some problems from this increasing and decreasing functions. Now we already know what is increasing function and what is decreasing functions. So recall their definition, that is what is increasing function, strictly increasing functions, decreasing functions and strictly decreasing functions. So if the value of x is increasing and the functional value is also increasing, that time we will call this increasing function. And if this value of x is increasing but the functional value is decreasing, that time we will call the function is decreasing function. So here is your first theorem. You can say this is a theorem. Like we already use this definition, that is by showing this first derivative is greater than 0, that time we will call the function is increasing function at a certain interval. Now we have to show it by mathematically that this first derivative is greater than 0 in a certain interval, that time the function is increasing in the certain interval. So what I have the function which is continuous on this closed interval a comma b, and it is differentiable on the open interval a comma b. And another thing I have, that is this first derivative is greater than 0. Then I have to show the function is increasing on this open interval. So if these two things hold, so let's see what I can apply. Here I am taking those 2 points x1, x2 in this open interval such that the value of x is increasing, that is x1 less than x2. Now since the function is continuous on the closed interval and differentiable on the open interval, so I can use this mean value theorem since it's satisfying the conditions of mean value theorem. So by the mean value theorem, I can assume that there exists a C between this open interval x1, x2. Now if in this open interval C exists, so by mean value theorem, what is f dash C? F dash C is given by f of x2 minus f of x1 by x2 minus x1. Now here I have that f dash x is greater than 0 on this open interval. So since this open interval x1, x2 contained in this open interval a comma b, so from here I can say in particularly f dash c is also greater than 0. Now if f dash is greater than 0, then put the value of f dash c here. So what you will find? This f of x2 minus f of x1 by x2 minus x1 is greater than 0. Now if it is greater than 0, then f of x2 minus f of x1 is also greater than 0. If we simplify it, we will find that f of x2 greater than f of x1. That is, the functional value is also increasing as the value of x is increasing. So from here I can say, since it's satisfying the condition of this increasing functions, so the function is increasing functions. So I have proved that if f dash x is greater than 0 in a certain interval, then the function is also increasing on this certain interval. So f dash x is greater than equal to 0 in a certain interval, that time the function is increasing function. And if it is just only greater than 0, time it is strictly increasing. That is, if it is greater than equal to 0, it is just increasing function, and if it is greater than 0 only, that is strictly increasing function. And one thing I can conclude from this derivative form, that is the function is greater than 0 all over this open interval a comma b except some finite points. Remember that except some finite number of points, that is finite number of points, the function is equal to, this first derivative is equal to 0. That time also the function is increasing functions. You can show it by previously, however we can show this using mean value theorem. You can also show these problems. So next, this function is continuous and differentiable, then f dash x is less than 0 on this open interval, then fx is decreasing functions. So f dash x is less than 0, I have another 2 things, that is the function is continuous on the closed interval and it is differentiable on the open interval. So in similar manner, however we will prove this increasing fx is increasing function on open interval. In a similar manner we will prove that the function is decreasing in this open interval. So as the previous one, let x1 x2 belongs to this open interval. So if x1 x2 belongs to this open interval and the function is satisfying the condition of mean value theorem, so I can use the mean value theorem. So we have to use the mean value theorem on this open interval x1 x2. That means there exists a number c in between this open interval x1 x2 such that f dash c is given by f of x2 minus f of x1 by x2 minus x1. Now here I have f dash x is less than 0. So if f dash x is less than 0 in this open interval a comma b and this open interval x1 x2 belongs to this open interval, that time in particularly we can say that f dash c is also less than 0 in this open interval. So if f dash c is less than 0, so what I can conclude from this, that is f of x2 minus f of x1 by x2 minus x1, that is the f dash value of f dash c is less than 0. From here if we simplify it, we will find that f of x2 less than f of x1, that is the functional value is decreasing as the value of x is increasing. So it will follow the definition of decreasing function. So the function is decreasing here. So we prove that the function is continuous on this closed interval, differentiable on the open interval, and if dash x is less than 0 on this open interval, then the function is decreasing functions. So without checking the points, we will check the function is increasing or decreasing by this first derivative is less than or greater than 0. So from this theorem what I can conclude, let's see, that is if f dash x is less than equal to 0, that time the function is decreasing on this open interval, and if it is less than 0 only, that is strictly decreasing on the open interval. I am repeating again, if it is less than equal to 0, it is decreasing function on this open interval. If f dash x is less than 0 only, that time it is strictly decreasing on this open interval. One more thing I can conclude from the theorem, that is f dash x is less than 0 in this open interval except some finite number of points where this f dash x is 0. Those points I am skipping, that at that point f dash x is 0. Otherwise the function is decreasing, that is f dash x is less than 0. That time also we will call the function is decreasing function on the open interval. So here first problem. Show that this function f(x) is strictly increasing for x greater than 0. So for solving any problem, first check what the information is given in your question and what you have to show. Here I have the function is given and the range of x is given, that is x greater than 0, and we need to show the function is strictly increasing. So for showing strictly increasing, what I have to apply, there is a first derivative is greater than 0. So let's check how to solve this type of problem. So given function is f of x is x minus 1 into e to the power x plus 1. So if we differentiate this function, we will get this f dash x. Now for this first part, x minus 1 into e to the power x, we have to use the rule of multiplication. So apply it, and the differentiation of constant is 0. So here is the differentiation. Simplify it, you will find the value of this first derivative is x e to the power x. Since x is positive I have taken, that is x greater than 0. Since this value is also greater than 0, we don't need to show it. We all know that this x e to the power x is greater than 0. So here I already show that f dash x is greater than 0 for all x greater than 0. Hence the function is strictly increasing functions for x greater than 0. Here is your next problem. The trigonometric function is given, that is f(x) is equal to cos square x. Now you have to show this is strictly decreasing function on this open interval 0 to pi by 2. Now what I have, in the same manner, just find it what the information given in this question and what you have to show. The function is given and this interval is given, where I have to show the function is strictly decreasing. For showing this strictly decreasing, what I have to do, that is f dash x is less than 0. So let's check how to solve this type of problem. So the given function is fx is equal to cos square x. So find the derivative of cos square x. First we have to apply the chain rule, that is for x to the power n and then again for cos x. So if we apply the chain rule here, if we will find that f dash x is 2 cos x and differentiation of cos x is minus sin x, and if we simplify it, the value of f dash x is minus sin 2x. Now look, this interval is first coordinate. Okay, so sin 2x is positive. We know that in first coordinate sin x is positive. So sin 2x is also positive in this open interval 0 to pi by 2. So from here, minus of a positive number, that is f dash x is less than 0 on this open interval. Hence the function is strictly decreasing on this open interval. So I think this types of problem very easy, where you have to just show the function is strictly increasing or decreasing, or just increasing or decreasing at a certain interval. So here is your next problem. The function is given log of sin x. Now you have to show this for this open interval 0 to pi by 2, the function is strictly increasing, and for pi by 2 to pi, this is strictly decreasing. So similar manner, first of all we need to find f dash x. So first find f dash x. Now log of sin x, again we have to use the chain rule. So I think all of you remember the chain rule, that is, first of all we have to differentiate log x and then sin of x. Then log x, differentiation of log x is 1 by x. So here it is 1 by sin x, and differentiation of sin x is cos x. So ultimately if we simplify it, we will find this cot x. Now this first coordinate, that is 0 to pi by 2, it's open interval, cot x is always positive. So if it is positive, then f dash x is greater than 0, hence it is strictly increasing on this open interval. Now second part, from this pi by 2 to pi open interval, that is second coordinate, and we all know that in second coordinate cot x is negative. So f dash x is less than 0, since the function is strictly decreasing function on this open interval, that is pi by 2 to pi. So moving to the next problem. Here the function is given, in a polynomial function is given. You have to show that this is neither increasing nor decreasing function. We know that if a function is increasing and decreasing, it's showing both the nature in a certain interval, then we can say the function is neither increasing nor decreasing. For showing it is increasing or decreasing, first we have to find the first derivative, that is f dash x. So let's find the first derivative of this polynomial function. The function is given x square minus x plus 1. Now if we find this derivative of this, that is x square is given by 2x, here it is, then x is 1 and differentiation of constant is 0. Now check here, if f dash x is greater than 0, that means it will imply that x is greater than half. That means in this open interval 0 to 1, if the value of x is greater than half, that time the function is increasing. That means in this open interval half and 1, the function is increasing. And in similar manner you can find if f dash x is less than 0, that time the range of x, that is from 0 to half, in this open interval the function is decreasing functions. So just find this derivative and check where it is greater than 0 and where it is less than 0. So for this greater than 0, the function is increasing, and for less than 0, the function is decreasing function. So in this interval 0 to 1, the function is increasing also and decreasing also. Hence it is neither increasing nor decreasing function. So next, find the interval on which the function, polynomial function again, is increasing and decreasing. So you need to find the intervals in R, that is the set of real number where the function is increasing and another is the function is decreasing. So first of all, the function is given like 2x cube minus 15x square plus 36x plus 6. Now find f dash x. that is differentiating this function with respect to x. So this is very easy to differentiate. Just we have to use this formula, that is x to the power n, differentiation of x to the power n. So apply this formula, we will find this equation 6x square minus 30x plus 36, and simplify it, you will find that 6 into x minus 3 into x minus 2. So if fx is increasing function, that time f dash x is greater than equal to 0. If it is greater than equal to 0, then this two factor x minus 3 and x minus 2, either both are positive or both are negative. So if this both are positive, x minus 3 and x minus 2 both are positive, that time we will find the value of x is greater than equal to 3. You can check, you can simplify it. That means if we check the range in R, that means from 3 to infinite, this interval x is belongs to this interval, and if these two numbers are negative, that means x is less than equal to 2, that means the range is minus infinite to 2. Now in this 2 interval, the function is increasing. So here is the range where the function is increasing. Now check, if the function is decreasing, that means f dash is less than equal to 0. So that means the product is less than equal to 0, that is x minus 3 into x minus 2 is less than equal to 0. Now when it is less than equal to 0, when the value of x is lying between 2 to 3, you can check, then the function is decreasing. So in between 2 to 3, that is interval 2 to 3, the function is decreasing function, otherwise the function is increasing function. So here is your homework. Here you need to find the intervals where the function is increasing and decreasing. First three problems are same, that is the increasing or decreasing interval you need to find, and the last one is you have to show this function is decreasing on this interval. I think these 4 questions are very easy. I think you can solve. If any doubt or any queries are there, you are free to ask. Thank you.